Okay, so welcome back. Like I said in chat, just let me know if anything gets fuzzy or it's it's buffering at all because I've been getting these. I don't know why. Last time it was the same deal, and just before, like just a few minutes ago, I kept getting a bunch of errors about the bandwidth being way too low. Um, So, question in chat about for number four, when you prove Heron's triangle area formula, can you use law of cosines? I won't limit what you can do to to prove it, although I will say you you don't have to. You don't have to do it that way. Although what you end up doing may be somewhat what you end up doing may be equivalent to the law of cosines, but you don't have to. You don't have to do it that way. But like I said, I won't put any limitations on what you do to show it. So remember Heron's formula. It's named after Heron. It might be due to Archimedes, but there's not definitive attribution to Archimedes, so it's typically attributed to Heron of Alexandria. Okay, so at the end of class last time, I had started talking about Indian mathematics. So I'd already mentioned that kind of the earliest examples were the this text called Rules of the Chord, which is kind of like the Rhiine papyrus and kind of similar to some of these early Sumerian tablets where things like Pythagorean triples are computed. So Pythagorean triples are computed, and there were some very, very basic geometric facts. And there's also this interesting bit where there's a connection between binary and poetry by translating syllables as either heavy or light and assigning them a 0 or 1 value so that every line of writing was basically a string of zeros and ones, right, as in binary, which could then be converted to decimals, and then conversions going in both directions were actually discussed in this context. And that was in about 800 BC. So early on in Indian mathematics, there's these interesting applications, but kind of the first big things that we see here that are kind of like on the level of the Greek mathematics, say around the time of the Pythagoreans, happens in about the 5th century AD with Aryabhata the Elder. So here's an interesting thing. So this is unlike the ancient Greeks. This is actually an example from Bhaskara. So I'll give you the following. Here is a statement of a problem from a text of Bhaskara. Okay, so there we go. The square root of half the number of bees in a swarm has flown out upon a jasmine bush. 8/9 of the swarm has remained behind, and a female bee flies about a male who is buzzing inside a lotus flower. In the night, allured by the flower's sweet odor, he went inside it, and now he is trapped. Tell me, most enchanting lady, the number of bees. So this is a very poetic way of asking for a solution to this equation. So what is interesting is that a lot of these Indian math texts, actually most of them that I'm going to be talking to, were written in verse. So they were written as if poetry was being written, which is definitely interesting. It's definitely an interesting way to pose algebraic problems, right? So that's also something that's very unlike the ancient Greeks who did not do that. So that example that I just showed was from Bhaskara. So we'll talk about him a little bit later. So Aryabhata the Elder, what is the main thing done here, or what's the main thing that he did? So he discussed. Actually, let me separate. I don't think. I think I have enough room to do this here. So, firstly, let me. There we go. So mostly his work was on arithmetic and algebra. and plane and spherical trigonometry. So I'll talk a little bit more about that later when I mention the math in Islamic countries, because this was there's a kind of a funny thing here when we talk about trigonometry, is that a lot of the named theorems in basic trigonometry were actually, in a sense, discovered for spherical trigonometry before Euclidean trigonometry. So like the law of sines, for instance, I believe was actually first stated for triangles on a sphere, before it was actually noticed that, oh yeah, this is actually true also for triangles in the plane. So anyway, mostly noted for arithmetic and algebra, and plane spherical trigonometry and astronomy. So he computed the sums. So the sums of powers 1 to the k plus 2 to the k and so on, plus n to the k. These sums for k equals 1, 2, and 3. All right, so when k is equal to 1, this, of course, is that Gaussian sum, right, that Gauss supposedly wowed his elementary school teacher by being able to sum this using the formula. So these sums Aryabhata computed. The other things contributed were quadratic and indeterminate equations. So he solved quadratic and indeterminate equations. The big thing is he was one of the first. He was among the first to use sine. So he defined the sine function in the following way. So before we saw that I believe it's Hipparchus had previously computed these sine tables. Of course, they were called chords. But we saw that those chord tables were actually computing sine. The way that Aryabhata used sine was sine of an angle A was defined to be the chord that we discussed before. It was the chord of 2A, all divided by 2. Okay, so I think I mentioned this previously using this double angle formula. The previous chord tables were computed in this way. Okay, and so this was sine. Let me look up really quickly. I had it written here. So I'm looking. Previously I had looked, and I believe this was also attributed to Aryabhata, but now I'm not actually. So it seems like technically, in a similar way to how this the chords that were computed by Hipparchus, and then Ptolemy also computed the same chords and included it in the Almagest. Aryabhata included these chords in what's called versine. Versine is 1 minus cosine. Okay. And so versine was also computed, but of course 1 minus cosine of A can also be written in terms of sine. So this is 2 times sine squared over, or times sine squared of A over 2. And so Aryabhata was not technically the first to compute these quantities, but to use them in a way approaching how these are computed in modern times, he was among the first. So he computed sine of A using the same methods I mentioned previously, computing these as lengths of chords defined in a certain way. And so from this, there's the notion of, so there's sine and versine. So these were the function and co-functions used by Indian mathematicians, where versine is 1 minus cosine of A. So it's almost sine and cosine, but it's sine and versine instead. So it's a little bit different, but you see that it's equivalent amounts of info because it's versine is just 1 minus cosine. Okay. All right, and so we're starting to get the trigonometry that you're used to, right? So we're getting closer to modern trigonometry, and by the time we finish our discussion of Islamic mathematics, we'll be there. So it was Islamic mathematicians that fully introduced sine, cosine, tangent, all the trig functions as we know them now were used and computed in the exact same way. So and of course, using this, he produced a sine table. That was very accurate. Okay. All right, so those are his big contributions. Again, some parts of this have been attributed to earlier Indian mathematicians, but we know for sure that he was among the first to use them in this way. Okay. All right. All right, so on to our second one, Brahmagupta. So Brahmagupta was a pretty impressive mathematician. So actually a lot of what we're going to discuss for the last two big names in Indian mathematics owe a lot to Brahmagupta because they essentially took his methods and generalized them. So Brahmagupta was responsible for several things. His biggest contribution, so he was born in 598 AD. He studied a Diophantine equation that is now called Pells Equation. So he studied the Diophantine equation, x squared minus n y squared is equal to 1. Okay. Now, this equation is called Pells equation. This is really a terrible name for this, but it has stuck, unfortunately, so we're kind of stuck with it. The reason that Pells equation is a really bad name for it is that the only reason it's called Pells equation is that Euler was writing to another mathematician, and in his correspondence he referred to this equation as Pells equation because he thought a mathematician by the name of John Pell. So John Pell was a mathematician that lived from 1610 to 1685. Pell had nothing to do with this equation. Euler was completely mistaken that he had anything to do with this equation, and so he called it Pell's equation for absolutely no reason, and that's why it's called Pell's equation. And so this is totally a misnomer. This really should be called probably Brahmagupta's equation. We have actually seen a version of this already. So we've seen a version of this because of this came up in the Pythagorean method for approximating square root of 2. So a type of equation like this was used to do that. But anyway, Brahmagupta studied this more generally for different values of n, and the method that he used to give solutions to this, and I'll show you some specific solutions for specific values of n. You can look at a nice table on Wikipedia as well for this thing, but I'll show you a nice example of a solution to this here in a second, because Bhaskara greatly improved this method, or Brahmagupta's method of solving this. But this was his main contribution, was studying this Diophantine equation. Okay, so I should say n. So n is it has to be positive and non-square integer. And if it is, then a solution xy that solves this equation for some specified n is related to an approximation of the square root of n by rational numbers. Okay, this is what we did when we originally did this for square root of 2. So we picked n to be 2 here and came up with fractions, or with solutions, pairs x and y that solve that. And of course we could get arbitrarily close to square root of 2 here by approximating it with rationals. So if you want to go back, you can look at that video. I can't remember the number of the video offhand, but we've seen this equation before. So a complete solution to this wasn't actually given until Lagrange did it in 1767. So a complete, rigorous solution was only given in 1767 by Lagrange. So Bhaskara gave a complete solution to this via something called the Chakravala method, which I'll talk about here in a second. But Lagrange was the first European to give a complete solution to this, and also it was completely rigorous, whereas Bhaskara's was a little bit more hand-wavy. But Bhaskara's method does provide a complete solution. Now, the issue is that while Lagrange's method, what Lagrange did, completely solves this equation, it's also very complicated. And for specific values of n, if you're actually coming up with some of these solutions, it's really complicated computationally. Whereas the method that Bhaskara ultimately came up with is a lot simpler. It's actually a pretty miraculous method. So anyway, this is the main thing that Brahmagupta did. He also studied the surface area and volume of pyramids and cones. So Brahmagupta also studied surface area and volume of pyramids and cones. Okay. And he used the square root of 10 as an approximation for pi. Okay. Another big thing that I've alluded to previously, especially when we were talking about Babylonians and Sumerians using placeholder symbols for 0, but not actually computing with 0. Brahmagupta was the first to give like a systematic way of dealing with 0 algebraically. Now, he had some issues dividing by 0, but he was able to do the basic things for working with 0 and with negative numbers. So Brahmagupta gave the first systematic way of dealing with 0 and with negative numbers. This is another big contribution. Okay. So much so that in one of his works called The Treasury of Mathematics, the Treasury of Mathematics is the work. This is by Henrietta Middenick, who provided a translation of Brahmagupta's, it's Brahma Spuita Siddhanta. I'm not even going to write that out. because I totally butchered it. Actually, maybe I should write it out because I totally butchered it. So, Brahmaspuita Siddhanta. So in this work, we get rules like negative times negative is positive. And negative times positive is negative. So these rules are actually written out explicitly in this work. So while he was perfectly capable of doing basic arithmetic with negative numbers and with zero, one thing that he had an issue with was dividing by zero. So dividing by zero, he wasn't really sure what to do. And so that was kind of an open question, or that was left open. One more thing that Brahmagupta did that was very impressive and relevant to your second homework. So Brahmagupta also proved the following formula. So the following formula is if A, B, C, and D are side lengths of a cyclic quadrilateral. What is that? So, i.e. one whose vertices all lie on a circle. Okay, so if A, B, C, D are side lengths of a cyclic quadrilateral, and S is A plus B plus C plus D over 2, then the area of the quadrilateral is square root of S minus A times S minus B times S minus C times S minus D. Where have you seen something like that? Well, this is a generalization of Heron's formula. Okay. So this is a generalization of Heron's formula. And you can think for a second about how this statement about quadrilaterals is connected to Heron's formula for triangles. Okay. Now, here's something that I should mention, and this also applies to what I'm going to say about the mathematics from Islamic countries. One thing to keep in mind is that a lot of these works are more similar to the pre-Greek math that was done by the Egyptians and Babylonians, where a lot of the results were not presented as proofs. Some of the methods outlined are basically equivalent to proofs in some way, but in many cases these works didn't actually include proofs. Okay, and so that's again a big distinction between Greek math and a lot of ancient math that was done by non-Greeks. was this proofs were very much a central part of Greek mathematics, whereas it wasn't necessarily a thing that was done by non-Greeks in many cases. So like I said, in some cases, the demonstration was basically equivalent to a proof, but it didn't proceed kind of axiomatically in the way kind of set forth by Euclid. Okay. All right. So that's quite a list of achievements. Brahmagupta is also responsible for some more things that I won't touch on, but if you're interested, you can have a look at the wiki article. Many things have been attributed to him, and I think there's actually been a lot of stuff recently. It's been shown that some things that got later attributed to Bhaskara were probably due to Brahmagupta, or at least known to Brahmagupta. Okay, so Mahavira. The main contribution is a basically tighter way of doing algebra with zero and negative numbers. So properties of algebra involving zero. So the classic statements that a plus 0 is a minus 0 is a times 0 is 0. Right? These things that you're used to were written out, stated by Mahavira. Again, Mahavira doesn't really know what to do with a divided by 0. This isn't worked out until Bhaskara. Also notes that negative numbers have no square root. Okay, now of course what is meant here is they have no real square root, right? But this is as far as I know, this is like the first mention of this. Okay, here's another example. So another example of interesting problem statements. So 1/4 of a herd of camels was seen in a forest. Twice the square root of that herd had moved on to the mountain slope. 3 times 5 camels, however, were found to remain on the riverbank. What is the number of that herd of camels? This is just a way of writing this equation. X over 4 plus 2 times root x plus 15 is equal to x. Okay, so solving that equation answers the question about that herd of camels. Okay, so moving on to the last big name and probably the arguably the most accomplished Indian mathematician prior to the modern era is Bhaskara. So Bhaskara lived from 1114 to roughly 1185. There have been a lot of things attributed to Bhaskara. So in fact, a lot of things that Bhaskara did were, like Archimedes, getting close to differential calculus, or in the case of Archimedes, he's getting close to integral calculus. But Bhaskara was getting very close to calculus in a similar fashion, and his works cover tons of topics. So basic arithmetic and algebra, reduction of fractions to common denominators, linear and quadratic equations, arithmetic and geometric progressions, interest and discount, triangles and quadrilaterals, approximations to pi, trig formulas, volumes of solids, indeterminate linear equations, combinations. He also gave a complete description of working with zero and basically an accounting of decimal notation. So he gives the rules that we're all familiar with. A plus or minus 0 is A. 0 squared is 0. 0 square root of 0 is 0. And he said A divided by 0, well, that's infinity. Right. Okay. So Bhaskara had no problems dividing by 0 that he could tell. The textbook doesn't mention this, but one of my favorite contributions of Bhaskara is what's called the Chakravala method. So it would take me too long to describe exactly how to use this method. This is a method used to solve Pells equation. Okay, so it generates solutions to Pells equation like this. Let me give you an example. Let's take n equal to 61. So this problem, finding integer solutions to this equation, so find integer solutions. Okay, and we can say just find positive integer solutions. You're squaring both of these things, so you don't care. But we'll say find positive integer solutions to this equation. We want to find the smallest ones. So it turns out there's infinitely many solutions, but we want to find, say, the smallest integer solutions to this equation. This was actually posed as a challenge by Fermat, I believe, in the 1600s. In Europe, and as I mentioned before, a solution to problems like this more generally wasn't finished in Europe until like 1767 by Lagrange. But Bhaskara actually came up with a way called the Chakravala method. So chakra means wheel. So this, if you see how the method works, you'll see why chakra is involved here, where the wheel comes in, because it's like this cyclic method of cranking around until you end up with the smallest integer solutions that you're looking for. So maybe looking at this, you don't think it's too nasty to find the smallest integer solution to this equation. So what is the smallest integer solution to this equation that you can find very easily with the Chakravala method? It actually is done it only takes a couple steps using the Chakravala method. So what's my solution? So smallest integer solution to this equation is given by x is, I can't even read the number, so I'm just going to write out the digits. So 1766319 and y is 226 980. Okay, so let's see if we can read this now. So 1,766,319,049 is x, and y is 226,153,980. Okay, so if you plug these in, you will see that they indeed solve the equation. This is the smallest integer solutions. Like I said, satisfactory answer to this wasn't given by European mathematicians until the 1700s. Bhaskara was able to do this. He actually did this not as a challenge. This was issued as a challenge by Fermat. Bhaskara did it as one of his examples. So when he was illustrating the Chakravala method. So this was one of the basic examples he did to show how this worked and how this could be done. Okay. So this is the Chakravala method is actually really kind of amazing. And maybe if I have time, once we get to like 18th century mathematics, once we get really to the 1800s, where we're going to switch gears and pick topics from various places, I may return here and show you how the Chakravala method works, because although this is something, it might seem complicated at first glance, it's actually something that doesn't require a whole lot of background to to do. So it only, yeah, I mean, it will require me some time. It'll probably require like a whole lecture to go over it, but it's pretty interesting. So this is one of Bhaskara's biggest and one of my favorite contributions. So that I believe is pretty much kind of all I wanted to mention. Some of the highlights of Indian mathematics during this time frame that we're covering, to allow European mathematics to rest a little bit. So next, as mentioned, is a discussion of mathematics in Islamic countries. So the textbook mentions that when it refers to Arab mathematicians, it's merely referring to the fact that most of these works were published in Arabic, while ethnically the mathematicians may have been Turks, Persians, or from wherever in the Muslim world at the time. But I will try to be more specific than that. So the big names, there are a lot of names to go through. I'm not saying that these are like the only three worth looking at. It's just that there were a ton of Islamic mathematicians that were doing work in very niche areas that technically their contribution was like one tiny theorem or fact, or technically maybe they didn't even really prove a single thing, but they did a lot of work on something. So for instance, easy example of this is there's a ton of Islamic mathematicians that did work on basically Euclid's parallel postulate and trying to prove it, or trying to come up with examples showing that it couldn't be proved or that it was false. And so technically, right, they didn't get anywhere with that because they weren't able to actually show it. This wasn't done until much, much later. This wasn't done until the middle of the 1800s. But they did a lot of work that technically showed that that it was at least possible to construct some of these things that they were trying to go for, but they were tossing them out as, oh, this is clearly ridiculous, right? Because without the parallel postulate, for instance, we wouldn't get that triangles have 180 degrees as their interior angle sum, things like that, which is true, but they were tossing these things aside. So there's a lot of there are a lot of contributions from a lot of different mathematicians during this time. Some of them weren't direct contributions. Some of them were contributions in the form of translating, because as we'll see, basically the thing that roused European mathematicians out of the Dark Ages of math was that they came into contact with translations. So Islamic translations of Greek mathematics texts they came into contact with, and this was kind of the catalyst that woke them up a little bit. Okay, and so a huge amount of gratitude is owed to just the translators, just not even the ones that necessarily contributed mathematically in any way, but just the translation of some of these Greek works. In fact, in many cases, these Arabic translations of the Greek works were the only source that was known until essentially modern times, and so they were basically the source for Europe's knowledge of some of these texts. They were like the only copies or the only versions of those texts in questions in many cases. Similar to the school in Alexandria, there was a school established in the 9th century called the House of Wisdom in Baghdad. So in the 9th century, there was a house of wisdom established in Baghdad. This essentially was the analog of the Alexandrian school, and it was basically the center of learning in the world. It kind of represented the greatest concentration of knowledge in the world at that time, until pretty much all the way up until its destruction during the Mongolian invasion of Baghdad. So, which happened in the 1200s. So, for about 400 years, it was basically the kind of the central like nexus of intellectual pursuits, pretty much in the world. So, this was established by Caliph Al-Ma'mun. I can't remember the year off the top of my head, but this House of Wisdom contained, as a result of decree, translations of many Greek texts. Okay, and it's from this that many of these mathematicians kind of began their mathematical pursuits. Okay, so as I said, because of this policy of preserving these Greek texts, this was basically why many of these Greek texts survived in the way that they did. As I'm going to include in the big info dump, a lot of what we know about Archimedes mathematically wasn't known until this Archimedes palimpsest was translated, but that wasn't until much later. So any ancient knowledge of Archimedes, any ancient knowledge of a lot of Greek math was due to these Arabic sources. So they were essentially responsible for preserving much of Greek mathematics in this way. So three mathematicians associated with this House of Wisdom, three big names here. First is Al-Khwarizmi. And so this Al-Khwarizmi lived about 830 AD. Second is Thabit ibn Qurra. It lived between 836 and 901. And Omar Khayyam, or Al-Khayyami, that lived between 1050 and 1123. Okay. So as I said, there are too many specific names to get into in this list that were responsible for not a huge density of works, but they had one or two things that they had shown. But this is kind of a nice highlights reel, pretty much. So Al-Khwarizmi, I don't know if you know this story. I like to repeat this story a lot whenever I'm in a class and that involves the explanation of any kind of algorithm. So Al-Khwarizmi's name is the source of the English word algorithm. Okay, so Al-Khwarizmi, his name was translated into English and was subsequently bastardized into the word algorithm. Okay, so the word algorithm is a very strange bastardization of the name Al-Khwarizmi. And this had to do with his description of an algorithm. So Al-Khwarizmi wrote a work. Let me see if I have the name of the text in front of me. Yeah. So the word algorithm specifically refers to the English translation of the Latin translation. And so the actual list, the actual text being read here. Oh, I'm having issues. So yeah, spoken has Al-Khwarizmi, or in the English translation of the Latin translation, spoken has algorithmi. Okay, is how that was rendered. Hence algorithm. As I said, this description of an algorithm happened in this big work, which I believe translates as like the compendium tome of balancing or something like that, which has to do with doing algebra. But even the word algebra itself, so he was responsible for this text. I think it actually has an even longer title than this. I think this is a shortened title. I'm not sure. I'd have to get my wife to translate it. So this is a terrible English transliteration here. So Hisab al-Jabr wal Mukabala, I think this is how this is said. So I want to focus on this al-Jabr. This is the root word for algebra. Okay, so this was his big work. I can't remember exactly how this translates, but it's like the tome of balancing, or I think it has to do something with balancing. Specifically, this word algebra, I think, has to do with balancing, which is referring to the operations that are done on equations. Okay, and hence algebra. Okay, and so the shortened version of this tome goes to algebra, and hence our name for algebra. So it wasn't actually. So this wasn't. It wasn't just names that that Al-Khwarizmi gave us. It was also so this treatment was kind of a very systematic treatment of algebra that involved a treatment of algebra including dealing with zeros and negative numbers. Not in this text, but later. So so Al-Khwarizmi's algebra was based on Brahmagupta's work. Okay, so it was based on the work of Brahmagupta. It was very influential. It technically didn't contain, in terms of solving equations, it didn't contain anything that wasn't known to even the ancient Babylonians or the ancient Greeks. But it was a systematic treatment. It had a few proofs, not too many, and it also contained an approximation for pi, but it didn't have a whole lot of rigorous reasoning behind it. Now, the style that Al-Khwarizmi used was influential in later Arabic texts on treatments of algebra. But in terms of the original contribution, there wasn't too much. It was an influential textbook, but it didn't contain anything too new. Okay, So the first big kind of name that contributed something really, really original was Thabit ibn Qurra. He basically is the father of trigonometry, one could say. So I've always found it funny. Maybe it has nothing to do with anything, but I found it funny that one of the big Arabic contributions to, say, like seafaring was the use of triangular sails. And I just wonder if that has anything to do with their pioneering work in trigonometry. I don't know. Could be total coincidence. Anyway, so as I mentioned previously, some of these early trig theorems were actually versions of them were shown for spherical trigonometry before they were actually shown in the plane. So it did work in spherical trigonometry. And plane trigonometry. So when I say spherical trigonometry, I mean triangles on a sphere, right? So triangles in the sense of the sides of the triangles are arcs of great circles. So he showed the law of sines. So he originally showed this for spherical trig, and then later showed it in plane trig. Okay. Also, by this time, I'm actually not sure off the top of my head if he was the one who originally introduced this, but by this time we had notions of sine theta, cosine theta, tan theta, modern trig functions. Used in the exact same way. Okay. Now, his interest in some of these things was maybe not super surprising, given that he belonged to a group of Neo-Pythagoreans. So I'll talk a little bit about that next time before finishing up this discussion and then moving on to what happens post Dark Ages as European mathematics kind of slowly crawls out of giant black hole of nothing. Okay, so anyway, I'll talk about that on Friday. So let me know if you have any more questions about the homework, and I will see you all Friday.